Welcome everyone, Professor Rosenthal here, and today we're going to tackle the concept of derivatives. And I've already mentioned to you a little bit about the history and how some of the ideas in mathematics developed, specifically the importance of understanding the rate of change, the instantaneous rate of change of a function. That was an important mathematical question that mathematicians of the 17th century were trying to tackle. But before we go into the definition and before I show you how they actually resolve this and how they solve the problem, I'd like to kind of step back a little bit and give you the overall appreciation and understanding of what a derivative is. So basically, one of my favorite authors, Keith Devlin, has once said that calculus is a set of techniques that scientists and engineers use to describe accurately the way things move, such as planets, whether it's space shuttles, missiles, electricity, radio waves, stock market prices, blood, the heart, and so on. So, and one of the branches of calculus is the differential calculus, where we talk mainly about the rate of change of something, and the techniques we're going to develop is going to apply to all of these fields. And one of my favorite textbooks of calculus, written by Stewart, in that textbook you can find the following paragraph, that rates of change occur in all the sciences. For example, an engineer may want to know the rate at which water flows in or out of a reservoir. An urban geographer may want to know the rate of change of population density. A meteorologist, the rate of change of atmospheric pressure. A psychologist, the rate of change when performance improves. What techniques are best for student learning, for instance. That would be a subject for education, but also for educational psychology. Sociologists may want to know the rate at which rumors spread. So all of those interesting and different phenomenon, whether it's current or electricity, which is the rate of flow of electrons, or whether it's in chemistry, rate of a reaction, even in biology, rate of growth or rate of flow of blood, and so forth. All of those are actually special cases of a single mathematical concept known as the derivative, which we're going to take a look at today. And finally, again, another paragraph from the Stewart textbook. And indeed, this is an illustration of the fact that power of mathematics lies in its abstractness. So math takes a single abstract mathematical concept, such as a derivative, and it can have different interpretations in each of the sciences. So once we develop the properties of a math concept, then it can be used in many different areas. And therefore, it's really a lot more efficient than trying to develop it in each and every science. So we just do it once. And the French mathematician Fourier has said it so nicely. He said the mathematics compares the most diverse phenomenon and discovers the secret analogies that unite them. So with that, we're going to now try to figure out what it is, specifically the formula, and then some examples. Now, remember, the main question that we're trying to answer here is figure out how to define instantaneous rate of change. So that's our major task today. But let's begin with something that we already know, the average rate of change. Okay? So let's look at this graph here where we have y equals f of x over the interval from a to b. And if your question had been, what is the average rate of change of this function over the interval from a to b, what would you say the answer is? Hopefully we already know that from algebra, but let me do a quick reminder. You would draw the secant line between those 2 points, and basically the slope of that line would be your rate of change. So what is the slope of this triangle, basically, or the slope of this line, which is defined, which is the hypotenuse of this triangle, right? So it will be rise over run. So to find the rate of change, average rate of change between those 2 points, so here's what we're going to do. To find the rise, that's basically the difference between these 2 points. So that's top minus bottom, f of b minus f of a. And what about run? From where to where do we go in the x direction? From a to b. So that distance will be right minus left point so that we end up with a positive distance, right? So b minus a. So this was our formula from algebra, rise over run, or in general, average rate of change of a function is f of b minus f of a over b minus a. So that's over the interval a to b. Now this is also known as the slope of the secant line because that line that we draw from there to there is known as the secant line. So that's average rate of change and the slope of the secant line. They're pretty much the same thing in this context. All right, so now we want to look at a specific situation where we want to attach some meaning to the function f of x, not just some abstract function, but it will make more sense, I think, we look at it in context, such as, let's think about the distance function. Y is our distance function, where t is in time, s is distance traveled, and let's just say s is in feet. Distance is feet. So what we're going to do is, okay, so imagine this distance function. So y-axis represents distance, x represents time. This function here is y equals s of t, representing an object moving in that time frame from, and initially in time equals 1 second. Let's say it was 20 feet from the original, from where it was at t equals 0. And then at t is equal to 3, it is 50 feet away. So this is our y equals to s of t function, the distance function. So my question to you is, what was the average rate of change of this function over the interval between 1 and 3 seconds? So based on what we just did above, this should be a relatively easy question, right? So what you need to determine is, all right, how far did this object travel? So rise over run. Rise will be the distance traveled. So between 1 and 3 seconds, this object traveled a total of 30 feet, right? 50 minus 20, that's 30. And how many seconds elapsed between 1 and 3 seconds? 3 minus 1 is 2 seconds. So to rise over run, 30 over 2, so that'll be 15. So, and what do you think will be the units? So we just did s of 3 minus s of 1. This is a little bit more detailed. Here I showed you the more intuitive explanation. So 50 minus 20 was 30 divided by 3 minus 1, which is 2. So 30 over 2 or 15. And what about the units? It'll be the units for the top over the units for the bottom. That is feet per seconds. Okay, so this is the average rate of change of that object over the interval between time equals 1 second to time equals to 3 seconds. Basically, what we just did there is we found the slope of the secant line joining those 2 points. So far, nothing new. We're reviewing things we've learned about average rate of change. But the thing is, you got to understand average rate of change really well to understand instantaneous rate of change. So I think this review was very important, so that we have a good solid understanding of that before we move on to instantaneous change. So the main question we have here is how to define instantaneous rate of change at the moment when time is equal to 3. Not between 1 and 3 like we had over here, but exactly at 3. Or it could have been asked as, what is the instantaneous rate of change? Let's say exactly at time is equal to 2 seconds. So like at this point, or at that point, at a single point, not between the 2 points. That is the question we're facing. Any thoughts? Think about this for a minute. If you like, pause the video. Give yourselves a few moments. How could one define the instantaneous change, not the average change? And it turns out there's a very simple explanation. One wonders, why did it take centuries for mathematicians to come up with this idea? So basically, we could make the time increments smaller and smaller. So for example, if you want to know exactly what happens at t is equal to 3, we could take a limit as time increments go to 0. So what we mean by that is, so you could find the rate of change between time is equal to 2 and 4, let's say, and then between 2 and 3.5, and between 2 and 3.2. And in each case, we know how to do it, right? Because we know how to find So you could find this slope of this line, then the slope of this line, then the slope of that line. As these points are getting closer and closer, eventually we're going to find the rate of change um, at the moment that we're trying to find. So the idea lies in letting the time increment get smaller and smaller. So shrinking the time interval and using the idea that we know how to find average rate of change, but do average rate of change in um, in a sequence of smaller and smaller intervals of time. So in other words, if we want to find, let's say specifically time is equal to 3, we're going to first find the rate of change between 3 and 3.5 seconds, then between 3 and 3.4, 3 and 3.3. You see where this is going, right? And you could make it smaller and smaller and smaller. Eventually, between 3 and 3.01, when you find that rate of change, well, it's almost going to be like, and you could do 3.000001. That will give you, and that limiting case will give you the derivative, the instantaneous rate of change at the point 3. So that is the key in determining the rate of change at a single point in time by taking a limit as time increment goes to 0. And here I have a little demonstration to make it a little bit more visual. Let's take a look. So here I have, let's see. Okay, so say this is our function f of x in red. And let's say that we want to find the derivative at the point 3. And the increment is h. So I'm going to make the increment smaller and smaller. So you see that point gets closer and closer and closer and closer. As that point gets closer and closer to the point that we're trying to find, in each case we find the average rate of change of this, find the average rate of change here and here and here. Eventually you see where it was, we're going to find ultimately the average rate of change at that point when we get super extremely close to that point. And that actually is called the tangent line. It's going to be as if we're finding the slope of the tangent line at that actual single point. So first we're going to do this through a table, and then we're going to do it analytically. In the future, we're going to use the analytical method more than the tabular method because it will turn out as more efficient. Okay, but in the beginning, let's first set up the table. And to help us understand the formula for the derivative, let's fill this out. So between 3 and 3.5 seconds, what is the average rate of change? So let's write the formula. Average rate of change is S of B minus S of A over B minus A. And between 3 and 3.5, so your B is 3.5 and your A is 3. So S of 3.5 minus S of 3 over the difference in the time increments. So the bottom is going to be just a half second, right? It's a half second increment. The top, to get the distance at 3.5, here you don't have a graph, but you have an equation. Just plug it in here. Okay, so plug 3.5 into that equation. Don't forget there's a little negative in front there. Okay, that's your distance at 3.5 seconds. And then to get this one, plug in 3 in that equation. So if we do that, and simplify it, we get the following. One of the easiest things you can do is enter your equation into your y equals screen on your graphing calculator and then go to the table feature. That way you can plug in a bunch of numbers all at once or back to back. So since you're going to fill up the whole table here, I would highly recommend that put your y1 equals negative 16x squared plus 500. Or if you're using Desmos, it also has a table feature there, and you can just plug in the x values. It will automatically give you the y values. And then plug in 3.5 for x, and then plug in 3 for x. You're going to get 304 and 356 respectively. So we want S of 3.5 minus S of 3, so in that order. And it's going to be a negative number. Don't be alarmed, because this object actually is going downwards. It's like a downward path on a parabola, so it's okay. We can have a negative rate of change, negative velocity, meaning the object is going downwards, basically. So if you will get this difference, Let's see what we get. So first of all, it's going to be negative, right? So it should be like negative 52 over zero point 0.5. And division by 1/2 is the same as multiplying by 2. So that's going to be negative 104. So that's the first answer. Fill in your table for the first answer, negative 104. And what about the units? It should be feet per second. Units for the top over units for the bottom. Now I'd like to give you a little bit of time and really to learn this to the best. At the very least, do like maybe a couple of these. And if you have a graphing calculator, you should be able to do this relatively quickly. Please do that because it will be interesting for you to see what's happening to the values, to see ultimately as we get really close to 3.01 or really get close, super close to 3 seconds, is there a pattern between these two values? So I'm going to give you a moment to fill the table and come back, check your answer, please. Okay, spoiler alert, I'm about to give all the answers, so hopefully you had a chance to think about this a little bit, fill in the table. So let's take a look. So if you did in 3.4 instead of this, and then this will still be 3, the bottom will be 0.4. If you did that ratio, you should have gotten negative 102.4. Next one, I got negative 100.8. The following one, again, if you did S of 3.2 minus S of 3 all over the difference in the time, which is 0.2, you should get this. And the next one is negative 97.6, and the last one I got was negative 96. And even there, the calculator, it shouldn't be exactly negative 96, but the calculator is rounding it to negative 96. So do we see a pattern where these values are approaching as time increment delta t goes towards 0? Well, it looks like they're approaching towards, they're getting smaller and smaller, but they're not going towards 0, right? They're like in the beginning, it moved a little bit more, but later on, it's moving less and less. Like from here to here, it only went from negative 97.6 to negative 96. So you could even try a closer value, like 3.0001. You're going to find that it's going to be almost exactly the same. It's not going to move that much after a certain point. And due to the rounding of the calculator, you're going to get negative 96. And units, once again, feet per seconds. So at the moment, we're saying with the numerical approach, it looks like the instantaneous rate of change is going to be negative 96. Now, if you're saying this was a lot of work, do we have to do this every time? The answer is not necessarily. If they don't ask you to fill out a table, you don't have to do this. There is actually a formula to find the derivative, which I'm about to show you. All right, so let's go ahead and quickly derive the formula, and then we're going to go ahead and use it. So right now, let's try to generalize it to any function f of x. We're going to try to find the derivative of this function at the point P. Okay. So what we do is use what we already know. We know how to find average rate of change. So first, we're going to find the average rate of change between P and Q. And from there, we're going to let the point Q get closer and closer and closer. In each case, we will be finding the slope of those secant lines. And ultimately, those secant lines are going to be approaching to this tangent line. And ultimately, in the limiting case, when the distance between P and Q go to 0, you're going to be left with the slope of the secant lines will approach the slope of the tangent line. And that is the instantaneous rate of change. So how do we derive a formula for this? So our point P is going to be x, and our point Q will be, so suppose you move a little bit away from x, say you move a distance of h units. Okay. In some books, instead of using h, they might use delta x. So a little incremental direction in the x direction. Our textbook or some other textbooks are using h, and it seems to be less complicated, so I'm going to use that notation. So we moved a little bit along the x-axis, a distance h units away. So the question is, first of all, what is the slope of the secant line in this generalized format? Okay, that shall be rise over run. So the rise is this distance, right? Think about what is that distance? This minus that, right? F of x plus h minus f of x. And what is run going to be here? It's this distance, how much you've moved in the x direction. And basically you went from here to here. the increment there was h units, right? So basically, the average rate of change over that interval will be the following: f of x plus h minus f of x over h. Now you might say that looks really familiar because you probably saw that in algebra, but you probably just learned it as if something to manipulate an algebraic expression without any meaning attached to it. But in calculus, it has a very special meaning. It's the slope of the secant line joining the points P and Q. But to find the instantaneous rate of change, what do you think we need to do to this quantity? Remember, the groundbreaking idea was to go from average rate to instantaneous. It was to make this interval shrink, make it smaller and smaller gradually. So we're taking a limit as which quantity vanishes? H, right? So take a limit as h goes to 0 of the above expression. And that is actually the answer. That is the formula for the instantaneous rate of change over the interval. As a matter of fact, I have a correction I need to make. Sorry. It's the instantaneous rate of change at the point x. And it has a special notation. It's f prime. So anytime you see f prime notation, just know that it means this. And it's also referred to as the derivative of a function f. So it gives us the rate of change at the point x. And this is the formula for it. Now, the alternate definition you might see in other books is the following. Limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Really, these are equivalent definitions. H doesn't really matter because ultimately it goes to 0. I could have used perhaps it's completely to say z as z goes to 0, right? But these are the two most commonly used notations, h or delta x. And once again, this is the derivative of the function f at the point x. All right. So let's take a quick look at the problem we just did with the table method, but this time using the formula. So this is our function. We're trying to find instantaneous rate of change at time is equal to 3. So let's remember, what is the formula to do that? But notice first I wrote in terms of x to make it easier for you because the formula for the derivative was stated in terms of x. So what is the derivative formula? F prime of x equals limit as h goes to 0, f of x plus h minus f of x over h. Remember, this is the formula for the derivative. Please memorize this. This is going to come up again, and you will need to know this for the test. So our f of x is this function. It's really, we have s prime of x equals the same question, but s of x plus h minus s of x, depending on the function. This is generally for any function. So let's start it. Excuse me. So replace x with x plus h. That's what this first quantity is telling us. To find the derivative, replace x with x plus h, which I did. So you take the x out, put the x plus h in the definition of the function. Minus f of x. So after the minus, I'm going to open a parenthesis and put the function itself in there. So we have f of x plus h over here, minus f of x. In this case, the function is s of x plus h minus s of x, and everything divided by h. Now, the rest is just algebra. We have to simplify this. So let's distribute our binomial and then distribute the negative 16. And there's going to be a lot of cancellations. So let me show you what happens when you do that. Remember, x plus h quantity square, you're going to need to FOIL that. That will be x squared plus 2xh plus h squared. And distribute the negative 16 that is in front of it. And so you distribute it one by one. So you'll get the following. Negative 16x squared minus 32xh minus 16h squared. And don't forget there's a plus 500 here. I just copied it over. Then distribute the negative sign here. So negative times negative 16x squared will be positive 16x squared. And then negative 500. Now cancel any opposites you might see at this point, such as negative 16x squared with the plus 16x squared. And negative 500 with the positive 500. And what we have left is the following. The bottom is still h. As I'm rewriting this, I'm going to factor out an h from the numerator as well. So I'll take out the h. You could actually take out a negative 16h, as you can see. So take out a negative 16h. From here, you're going to have 2x, and from here, plus h. If you have any doubts, multiply this again, and you'll get those two quantities. And remember, you're dividing by h, so now the h's can be canceled because they are factors. So we're left with negative 16 times quantity 2x plus h. Remember to take a limit at this point as h goes to 0. And notice up until this step, I kept my limit notation, right? Only at this level you can drop it because you are now taking a limit. Of all the other places, limit was saying, we're going to take a limit eventually as h goes to 0, but now we're taking it. So take the limit, so h disappears, and we're going to get negative 16 times 2x. That's negative 32x. This is the equation for the derivative at any x value. If you want to know what happens at x is equal to 3, simply plug in 3 for x in the above equation, and you get negative 96. Now, does it look familiar to us, negative 96? Hopefully, right? We got that same answer in the previous page, but we used a tabular approach. You might say, well, this wasn't that short either, right? It took us a little bit of time to get there, but what if I asked you find the velocity or the instantaneous rate of change at the 3rd second, at the 4th second, the 5th second, etc. I gave you like 5 different values, let's say, okay? With the other approach, you have to do a separate table every single time. With this approach, you get it once and for all, okay? And if we write back in the original variable, the time variable, so the derivative is negative 32t. So you get the derivative once and for all. And then if I say, what is the derivative at 3? Plug in a 3. Derivative at 2? Plug in a 2. At 1? Plug in a 1. So you can get all of those other values instantly, whereas the other approach, you had to create a new table. So as you can see, that will actually be a lot more work if you had to insert more than just one value. And this approach, we like it better because the other one was an approximation. We consider this to be an exact approach. It's analytical, and it doesn't really rely on how the calculator will round quantities. It's once and for all. And there's another beauty about this formula, and it will apply to any function. It doesn't have to be just this function. So for any function, it will work because the formula is generalized now, and it will work for any point x, not just x equals to 3 or a specific value. So in the next segment, we're going to do more examples. I know this is a little bit complicated at first, but let me give you the good news before I end this segment. Not in the next segment, but the following one. We're going to talk about the shortcut rules, and actually problems are going to get a lot easier. So why are we doing it with the long method? Because we want you to understand where the shortcut rules are coming from. And on the test, I usually put like 1 or 2 questions saying, show me the derivative using the limit definition. And for the other ones, you would be allowed to use the shortcut methods. So first, we're going to do a few more examples using the limit definition in the next segment. See you soon.